this field, in fact. And this is one of the things that will become apparent during this course. As when I took these lectures, at the time we didn't yet have this book, it was already old also, but we had this reader based on which is this book later appeared. Okay, there were also challenges, but right now many more challenges and interesting things to do in this field. Yeah? But gradually I will tell you more about that. You just started, many of you have just arrived, I guess, here, more or less, yeah, this country. Okay. So the way we work during the lectures here is that most of us, at least I want to do that. Hello. I want to make the threshold for having interaction here as low as possible. That doesn't mean that I want you to interrupt me again and again and again all the time. But if there are things that are not clear to you, please raise your hand and ask. If I think it's not so interesting for the entire group, I can come back to that during the break. Yeah? But what I don't want is that you're afraid to ask things because you think it is maybe stupid or you make a bad impression. It's very difficult to make, in that way, a bad impression on me. If you keep silent all the time, then you make a bad impression. Okay? I know that even while saying this, there are cultures in which this is not done, and I cannot change this from one day to the other. I appreciate that. But try to be active, try to understand things. Because for me, it's not important to memorize the things in the book. Yeah, so some students sometimes come to me during the oral exam. It's an oral exam for this. Yeah, on page 37 of the book, it is written that. Think, okay, but what do you think about this? Do you agree? And then sometimes, not sometimes, often I get a little shocked there in the student. Now they have to say something. But this is the professor. Professor Krug who wrote this book. He's not infallible. And we expect you to be critical towards the things we tell you. Always question these things. This is a scientific institute, not just a kindergarten. So, I joke a little bit. I like to joke, but there's a lot of seriousness behind. Yeah? So be critical. Yeah? And you will see that even I will make sometimes mistakes here. Sometimes on purpose, just to challenge you. Sometimes because I'm just a human being like you. Okay? So raise your hand. There's this photograph here. Can you see what it is? A distribution transformer. Yeah. Any idea where I made this photograph?
India.
No. Do you think I could have made this photograph here in the Netherlands? What do you think? What's your feeling? No, huh? No.
Too messy.
Too messy. When I tell you that this photograph was made in a land where nothing is messy, everything is very, very organized, this is a hint, Japan. Huh? So, even in a country that's so well organized, everything is on time. You know all the stories about the bullet train, Shinkansen. It's amazing. But if you walk through the center of Kyoto, this is the way they take care of the electricity supply. And they are able to ensure a very high reliability as well. So, the things you need to do to ensure that very high reliability, especially with components that grow older and older and older, this is one of the things that I will shed some light on during these lectures. Okay. We will have roughly 12 meetings here together, and you may ask yourself, you may ask me, what can you expect from these lectures? Well, really this is about the basics. This is the first series of lectures in high voltage, and you should get the basic knowledge on high voltage about insulating systems. Okay. And we depend very heavily on the application of knowledge you should have gotten during your bachelor, which is electric fields, Maxwell's equations. I also taught in the bachelor, and at that time I told students, maybe you don't like Maxwell's equations, but when you go in the direction of telecom or power engineering, they will come back to you, and you will see why you needed to invest time in understanding these laws. So you will see. For us, and that's why this is a technical university, not a normal university, and so there's more of a link with application and industry. Yeah. So what I want is that you, as qualified engineers, you can do science or technical issues or whatever, someone can approach you, ask a question, a basic question. Okay, I designed this cable termination. What do you think about it? Okay, what I want you then to be able to do is to make a first rough evaluation of this thing without having to resort to computers, books, whatever. Yeah? But because this is what people expect from us in practice. We are highly qualified, high voltage engineers. They expect us to say something without asking somebody else. Of course, if you want, the next level is to go in depth. Then of course you're allowed to look in the books, to make some simulations or whatever. But I always use it, let's say the beer filter, beer mat, you know what it is, these round things? I want you to be able to explain roughly the back of a beer mat, how things work in this field. Yeah? So this is highly challenging, but I think it's very important. I'm not against computers or everything, yeah, but I guess you get the picture. This is what I want you to be able to have the basic understanding here. Now, how to study? We have this series of lectures. I always try to give my lectures. I improvise a lot to explain to you why things are important, why you should do this, why you should do that. Not just because you have to take this course. It should make sense. Everything. And I will, of course, supply you with basic knowledge. You have the opportunity to ask me questions. You can also, we have a beautiful high voltage lab, so we can show you the real thing in our lab. And we will make ample use of that. So in, what is it? About 20 minutes time, we will walk as a group to the high voltage lab and we get our first demonstration, demonstrating the phenomenon. And we will do that every single meeting, either halfway or at the end. It's very important for me to see things, to be able to understand them. Then of course you have to work on it yourself, you have to study. And this is a story I've been telling for more than 20 years. It makes sense to, after the lecture, to go through the book. It doesn't take hours. You have to see, did I understand what is the main thing that Peter wanted to tell us here? And in preparation for the next time, just go quickly through it, do the same thing. Even if it's 5 minutes, it doesn't have to take a long time. This is important, but I know I was a student once, so I know how it is, but still I advise you to work this way. Don't start studying just before the exam. Okay, then there are handouts, because this book was written in the 90s, before many of you were born, I guess. So, let's not exaggerate. Before some of you were born. And anyway, things change also in this field. It's not standard. So the things that change will appear in the handouts. and so on. So please, and the handouts, you know where you can find them. I say to the students first. Blackboard. Yeah.
So the readers section.
I got just go to the Blackboard page of this course and put on the which heading. If no, I will check also myself. They should be there. Yeah. Or last year's, but it's roughly the same. Yeah. There's also the errata, because there are some corrections to what you find in the book. Please also download, print them, and put them right in the correct pages in the book. Yeah? Okay. That's about that. Any questions about that?
Is that the man who was here first said that the book was important to buy for us?
Yeah.
Let's say. So where can we find them? In it's like 25 euros, is it?
Yeah. Yeah. Where you can find the man with the books.
Yeah,
that's
for
a question.
example, or just
Yeah.
buy the books. Yeah. Where can we buy the books?
You have to. It's a long walk, but you go to the lower building, the end of the corridor, ground floor, the room to the left. Paul van Mes, he's the high voltage lab manager. Yeah. I guess it also next week we will bring some books here, so that you will have to go there. But if you want to have access to the book before next week's meeting, then I advise you to go over there. Yeah. It really makes sense to buy the book. And, 25 euros. There are more expensive books that you could buy. So. Any more? Yeah?
Games out for the Norse.
Very good. I almost forgot the PAO before. What I usually do is I share a Dropbox folder. I know that in some companies it's not allowed to make use of Dropbox. Anyone here of PAO has a problem with it? And I cannot give you access to Blackboard, so well, we have to figure out how we do that. We find a way otherwise. And always use old-fashioned email. Yeah. But we need to take care of that. And for the others, I need to have your email address, then I can send you an invitation to join the Dropbox. That's not for the students, but for the people from industry. It's a nice bridge because the students may wonder why are there people from industry here, old students, so to speak. This is a post-academic course as well. It's in parallel. We do two things at the same time. And we've done this since the days of Professor Kreuger, who wrote these books. He was my professor. And it makes sense because people from industry, they're dealing from day to day with the real problems and challenges that you are supposed to solve with your bag of knowledge later on. So they will ask different kinds of questions to me than you, and you can and should learn from that. And you can have interaction with them, because I can tell you most companies in this field are hunting for good young engineers. Not ready yet, but it doesn't hurt in creating some kind of relation with industries and knowing where you could have a career later on. For the people from industry, it's also good to meet the young people, the future. So for them, they're looking at where are our new how do you say engineers. What are their wishes, problems, and being still a student, you have a more, let's say, scientific approach at this point in time than the people from industry. That's more applied. So the confrontation of the two has proved to be very interesting last 25 years. So that's why. Okay. What else? Yeah, something very important. The schedule. We have some spare meetings scheduled always, because things can happen that I have to skip a lecture. We have a meeting scheduled the 14th of November. It's in the second quarter. Yeah. This meeting will be cancelled, to put it shortly. But it means that we schedule directly a new meeting on the 12th of December. It was already, for people from PAL, it was already in your list, I think. So the 14th of November will be cancelled. That's the only change. Okay. For the students, you should do an exam after the series of lectures. It's an oral exam. What you do is you contact the secretary, and she has access to my agenda, my calendar, and she can suggest a date for your exam. It can be anywhere in the year. You're not bound to exam periods or whatsoever. That's nice, but please be advised that I'm a pretty busy person. I'm only here 2 days in a week, and we have lots of students who need to do the exam. So don't expect that if you go to the secretary 1 week before you want to do the exam that there's still an opening, because I can guarantee you there will not be an opening. It's the way it is, but I want you to know that. Okay? It takes 1 hour to do your exam. Okay? That's all clear? Yeah?
I got a question. There are 2 exam dates. There is one after the first quarter and then after the second quarter. So it will be only after the second quarter.
No, whenever you're ready and I'm available. So it's not linked to any exam period or whatever.
Okay, so there will be only one exam. Because
There will be one exam.
okay, in Bloodword it's like there will be 2 things.
Really?
Yeah, there are 2 red dots. So this is what I'm asking.
No. No, only one. One is enough. Yeah. It could be 2 if you fail, but it's,
That's what the program overview says, that there are 2 exams through the 2 quarters, and so when will the credit be awarded for this high voltage construction after the second quarter?
once I put your grade in Osiris, our system, then it will be taken into account for that particular quarter or semester. But when is the time to do the exam? January, February, I would say, because the last lectures are in December. You know, we have Christmas and everything, and so. Yeah. Okay. Good. Wow, this is a very, very long introduction. But at least I want you to know what you can expect and how things are organized. So let's talk high voltage now, because that's what we're here for. So you may ask a very basic question, what is high voltage? Where does it start? 1, 2, 3,000, 10,000, 100,000, 1 megavolt. At the time, my professor who wrote the book, Professor Keuger, said up to 1,000 volt. Yeah, it's not real high voltage, because if you want to make a high voltage cable for 1 kilovolt, 1,000 volt, you need a piece of copper, and then you need to take some toilet paper and some olive oil or vegetable oil, and like this, and then maybe some copper tape around. Will live forever. Yeah. So it's very easy. There are no challenges. Why are there no challenges? Because, and this is essential, and we'll come back again and again and again, the electric field is very, very low. Because one of the things you will learn is not so much the voltage, that's important, but the electric field. But more about that later. Now, in real life, in utilities, in electricity power supply system, we consider any voltage between roughly 10 kilovolt, 10,000 volts, and 30 kilovolt, 30,000 volts to be medium voltage. That is the level at which normally electricity is being distributed inside urban areas and so on. When you go to transport of electricity longer distances, we speak about 50 kilovolt all the way to 1000 kilovolt or even more. Where do you think in the world, in fact, we use the highest voltages for transport? Which country?
Recently in India, 1200 kilowatt.
1200. Yeah. Well, has it already been realized or are these
Yeah.
plans?
Tested and it is in implementation.
Oh, okay. So you beat China then? No? Because what is the highest voltage in China right now?
After this implementation, it will be the highest.
You're not Chinese, so you cannot answer that. But what is it right now in China? Any idea?
800 kilowatt.
800 kilovolt, very well. But quite soon it will become 1000 kilovolt AC, in fact. Why are these voltages so high? And why especially in India and China?
Long distances.
Long distance transport. Why do we need high voltage then?
Reduce the losses.
To reduce the losses, yeah. Because losses are related to the current through the conductor. I square times the resistance of the conductor. So to create a certain amount of power that you want to transport, it's U voltage times current. So increase voltage, reduce current, and your losses go down with this current. So very simple. But that's not yet the full explanation, because the fact that China and India are quite big doesn't necessarily mean that these transmission lines need to be very long. Why not generate all the power close to the places where everybody lives? I guess that makes a lot of sense. Where's the energy coming from in China? The electricity, where is it being generated? Hydroelectric, a lot in the mountains. There's not so many people living there, so we have thousands of kilometers to bridge. And in India, it's more or less the same. There are other reasons for making these ultra-long connections, is that linking different parts of the network and making it more stable and creating some kind of virtual reserve capacity in the network. Okay, what is the highest transmission voltage here in the Netherlands? Dutch students stay quiet for a moment.
380.
Sorry? 380. Maybe if the Dutch don't know, but it's 380 kilovolt. Yeah. Okay. You should realize that once you get to higher and higher voltages, the complexity of the design and implementation and reliability increases exponentially. So whenever a step is made to a higher voltages, there's some kind of a shock in our community. Last week, ABB, ABB, one of the big companies in this field, announced that they produced the first 500 kilovolt HVDC polymeric type cable system. And this is a major leap in this area. Not just because the voltage is so high, but these systems, they need to live and they need to be operated continuously for quite some time. How much time?
20 years.
Well, it's more 30-40 than 20-30, but yeah. No. Imagine that you drive a car for 30 years, continue. Yeah, I don't know why you should do that, but try to imagine, but for 30 years continuously, no car would be able to do that. No? So, okay. So I mentioned already a few things. It's more the electric field. That's important. If you go to higher voltages, the problems increase because usually also the electric fields increase. Lifetime is very important. The reliability. These are some very, very old pictures, but you get the picture by looking at them. This is the classic way the electricity supply chain is organized. To the left, production unit or generation unit, then you have transmission at a higher voltage. You explained to me why. Then we get go down in medium voltage, then we get the distribution. That's the classic way. Most of the time it's still like this. I guess you've all heard of smart grid. In a smart grid, we can go in all directions. Power flow can also go from the right to the left, but not necessarily in this scheme. If you consider, let's say, the city center, where more and more people have solar panels on their roofs, the power flow can also go from, in fact I have solar panels, and go from my house into the grid. So this is all changing. But at the high voltage level, no real changes right now. You can argue, yeah, at the high voltage level, what has changed, that you see more submarine long distance connections, and you see that we have the connections to offshore wind farms at high voltage. These things have changed. But this whole idea of smart grid is not so clear at the real high voltages. Some examples of this is called high voltage constructions of this course. And the word constructions is very important because we can just focus on materials. So let's say this is a material, or we say insulating material, or a dielectric also. And of course, it needs to be very strong, meaning that we can insulate a very high voltage across. Yeah? And I can show you that you should take a well-known material, polyethylene. It's used mainly for high voltage cables. And if you take a very small piece of that, very thin, yeah, much thinner than this, maybe, let's say we go down maybe to some tens of microns thick, the electric field that can be contained for some time in this material can be maybe 800 kilovolt per millimeter, 800,000 volt. Just insulated by 1 millimeter of insulating material. This is really amazing. Of course, it's hard to imagine what 800 kilovolt means across this distance. But this is the top level, only when you have extremely thin laboratory samples. If you take the step to a construction, high voltage cable, or transformer, or switch gear, things change. You no longer need, can consider just this single material. You have a system, construction, different materials that get together. And the amount of material is much larger, of course. We don't talk about this thickness anymore. So we have a huge amount of material. All of this will result in an electric field that we can allow, which goes down, let's say, from 800 to maybe 15 kilovolt per millimeter. And that is because we're no longer talking about the material, lab things, but real things and constructions. Okay, so here we have some of the constructions in the grid. We have, of course, we need means of measuring voltage and current. So we have voltage transformers. We have the transformers themselves, and on top of the transformers, you see these things like this. Yeah? They're called bushings. We need these things in order to come in with the voltage or get out with the voltage in a proper way. By the end of this course, you know why they look like that, and how you could design a basic bushing work yourself. But you, more importantly, you know the why behind things. Net filters, whatever, some more. When you have lots of open air space in some countries, we have here, we don't in the Netherlands. We find these open air substations.
Could you go back?
Yeah.
The net filter, is that a wave trap or is it something different?
Sorry?
The net filter,
Yeah.
is it similar to wave traps or is it something else?
You need net in HVDC systems, for instance. You cannot do without the filter. Yeah. So yeah. But by the way, because I'm very enthusiastic about HVDC and things that need to be done there, but we're not going to focus on HVDC here in this course. It's too complicated. There's another course on that. So this will be mainly high voltage AC. Okay. Substation, switching and distribution, everything. You use air mainly as an insulating system. You need lots of air to insulate. Do you know what is the breakdown field strength in terms of kilovolts per millimeter of air? I mentioned in a high voltage cable we allow 15 kilovolt per millimeter, maybe 20. What can we allow here in the air here?
Isn't it 3?
Yeah, it's close to 3. Yeah, but that's the breakdown value, so we have to stay way below. So air is not a good insulator, as it is here. We will see later on that we can do something to the air in order to make it a better insulator. Overhead lines, it's not so clear everything. See these high voltage towers here? They don't look like high voltage towers, these in fact. Yeah? This is a new concept, which can be, takes much less space. Yeah? And the resulting electromagnetic fields should be lower. This is a new concept. TenneT, the Dutch transmission system operator, has positioned these poles here, not far from Delft, in fact. You can see that. Yeah? And then, of course, you have the closed substations. Yeah? The big difference is that in principle you could just wander around here. Of course, you're not allowed, but because all the field, electric field of course, is contained in these greenish tubes, it's SF6 field, yeah. And the outside should be grounded. It's very compact. Why is it so compact? Because here we do no longer rely on air being the insulating system, but SF6, which is an insulating gas, but also under pressure. And we see that if we increase the pressure of the gas, also of air, we make it stronger, electrically speaking. So that's why we see compressed gas systems in this field. And many of the switch gear, the switch energy, is SF6 based. We rely a lot on these systems, and we get a lot of benefits from pressurizing this gas. Maybe for 400 kV we need roughly maybe this insulating distance, 400 kilovolt roughly. That's a lot. Of course, there's always the other side of the medal. These systems are quite sensitive to the presence of defects. Defects for the lamine can be maybe a piece of aluminum left there wandering about, can lead to a full flashover breakdown. Why would there be a piece of aluminum lying around?
During maintenance activity
or installation, yeah, with aluminum conductors also. These are huge systems, so there's a finite probability that something is left behind there. Also, complete tools are sometimes left behind, in fact, but yeah. You can imagine that that could lead to a failure, but also very, very small particles can lead to failure. High voltage, there's not much to be seen here, but high voltage cable terminations. High voltage cables, you cannot just cut the ends and then connect them to a transformer or anything. Some of you I see shaking your head, but I know some of you don't know that yet. You should properly terminate high voltage cables. Because if you don't, it will go totally wrong. One of the things you will know at the end of the course is why you cannot just cut cable ends and connect them to a transformer or anything else. What would happen?
Is it because of the reverberation of the waves?
No. I'm tempted, of course, to explain right now what I want. So should be a reason for you to come back here. No, otherwise it will become a total mess. But this is one of the things you will learn, yeah, in this course, and then how to terminate these cables. This is the high voltage cable that everybody uses right now for new high voltage AC cables and gradually also high voltage DC cables. You see, that's not just one material. At least you see different colors here. Of course, the copper core is thick, and also at the end of the course, I make you many promises, but you can keep me to them. But the things that you will learn, you will understand the functions of the different materials and layers that you see here. Because you see, the copper, okay, it's clear, I guess, to transport the energy. And it needs to be thick, otherwise you have too many losses. But there are some black layers here, maybe difficult to see. The white is the insulation. Easy to understand that you need them, but there are also black layers. Why are they there? These are things you want. Sorry?
Encapsulated field?
Yeah. It's funny. It's okay. These are questions that you don't have to answer right now. But it's okay. Don't understand me wrong. But these are the things you will learn. You understand? So we have different types of cables. The classic cables are being produced with paper and oil. Paper is the insulating material. If you look at paper is really like a tree. Processed tree, that is good. If you would use paper and use that to wind around the copper core, you could argue I also have a high voltage cable. The paper is the insulation. But if you would look more closely to the paper, you will see that it's very porous, meaning that there's a lot of air inside. And air was a bad insulator, remember? So you need to get rid of the air. That's one of our biggest challenges, in fact. But, so you impregnate with a better insulating system, which is oil in this case. It's the old way of insulating. But when you start using oil in a cable, sometimes, let's say a submarine cable, it's a ship on an anchor. It can happen. Probability is not so high, but that you hit a cable and that there's oil spillage in the ocean. We're very much afraid, and we should be nowadays, because it has it affects the environment very much. We don't want oil in the environment. Same thing is true and much stronger on the land, because most of the cables are, of course, here in the ground. If there's a drag line going again and hitting one of these cables, okay, then you get some oil spillage. This is, by the way, the main cause of failures of high voltage of cables, especially medium voltage cables. It's not that like there was a defect inside the insulation or whatever. No, because it's again a drag line. You will learn about interesting things that we call electrical trees. Electrical trees is a failure mechanism. So it's, in a way, for me, it's nice to see, to have a look at things that went wrong, exploded transformers, all these things, because that's exactly the thing we want to prevent. So we should know about what are the things, the events that could lead to such a thing. So we need to know also about physics, about chemistry, about aging processes, routes to failure, all these things. It's very important. Also, you will get a basic understanding of the things that lead to failure. Power transformer can be as big as a house and even bigger. Yeah. And make a small sidestep, and then we walk to the lab for the demonstration. In the Netherlands, we have transformer manufacturer Smit in the center of the city of Nijmegen, and it's a great, it's a high-tech transformer company. I think it ranges along the best in the world. Well, it's not very big, but they can make transformers up to 800 kilovolt level. And once in a while, the Students Association here, Sterkström Dispute, SSD, they organize excursions, maybe to Smit or to Brisbane cable manufacturer or wherever. I advise all of you to go there. It's extremely interesting, and normally you don't have the opportunity to have a look inside. And don't be misled. Although, when was the transformer invented? Anybody knows?
Westinghouse.
Sorry?
George Westinghouse.
Yeah, but when was that?
19th century. And
Many years ago. So you can argue what's new about it. But then you should visit these companies. You'll see what is new and why these systems are so special. So that's my advice to you. Participate in these excursions. So let's make a break now. Walk to the lab. Please do not walk too slowly. Yeah, I'm sorry to say, because sometimes I have students, they look like, behave like they're 70, 80, 90 years old. They go so slow, and I don't want to lose too much time. So you don't have to run, but I will, if I have the key, I will close the room, so you can leave everything behind. Yeah. Follow me, and I'm on that.